Hi everyone. Through this class, we are going to study about the design procedure of IIR Butterworth digital filter. The analog filter is designed by approximating the ideal frequency response of the filter using an error function. There are different approximation methods developed for this. The popular among them are Butterworth and Chebyshev approximation. First, we consider the design of low-pass digital Butterworth filter. The popular methods of designing IIR digital filter involves the design of equivalent analog filter and then converting the analog filter to digital filter. Hence, to design a Butterworth IIR digital filter, first an analog Butterworth filter transfer function is determined using the given specification. Then the analog filter transfer function is converted to a digital filter transfer function by using either impulse invariant transformation or bilinear transformation. The analog Butterworth filter is designed by approximating the ideal analog filter frequency response h of j omega using an error function. The error function is selected such that the magnitude is maximally flat in the passband and monotonically decreasing in the stopband. The magnitude response of low-pass filter obtained by this approximation is given by modulus of h of j omega square equal to 1 by 1 plus omega by omega c raised to 2n. Since modulus of h of j omega square is equal to h of j omega into h star of j omega, that is equal to h of j omega into h of minus j omega, we get it as h of j omega into h of minus j omega equal to 1 by 1 plus omega by omega c raised to 2n. We know that the frequency response h of j omega of an analog filter is obtained by putting s equal to j omega and omega by s by j. Therefore, h of s into h of minus s equal to 1 by 1 plus s by j divided by omega c raised to 2n. Therefore, h of s into h of minus s equal to 1 by 1 plus s by j divided by omega c raised to 2n. That is equal to 1 by 1 plus, here the power 2 we can take inside, then it is equal to s square divided by j square omega c square whole raised to n. S by omega c is replaced by Sn, that is by letting omega c equal to 1 radian per second. The transfer function is called normalized transfer function. Therefore, normalized transfer function h of Sn into h of minus Sn equal to 1 by 1 plus minus Sn square whole raised to n. This transfer function will have 2n poles which are given by roots of the denominator polynomial. It can be shown that the poles of the transfer function symmetrically lies on the unit circle in S-plane with angular spacing of pi by n. The magnitude response of Butterworth low-pass filter for various n values are shown here. We can see that when n increases here from 1 to 10, we can see that the graph is more close to the ideal one. Next, we consider the properties of Butterworth filters. First one, the Butterworth filters are all pole designs. That is, the zeros of the filters exist at infinity. Second one, at the cutoff frequency omega c, the magnitude of normalized Butterworth filter is 1 by root 2. That is, modulus of h of j omega equal to 1 by root 2 equal to 0.707. Hence, the dB magnitude at the cutoff frequency will be 3 dB less than the maximum value. Third property, the filter order n completely specifies the filter. Fourth one, The magnitude is maximally flat at the origin. Fifth property, the magnitude is monotonically decreasing function of omega. Sixth one, the magnitude response approaches the ideal response as the value n increases. Next, we consider the design procedure for low-pass digital Butterworth IIR filter. First step is choose either bilinear or impulse invariant transformation and determine the specifications of equivalent analog filter. The gain or attenuation of analog filter is same as digital filter. The bandedge frequencies are calculated using following equations. For bilinear transformation, passband edge analog frequency corresponding to digital frequency omega p is omega p equal to 2 by t tan omega p by 2. And stop band edge frequency corresponding to digital frequency omega s is omega s equal to 2 by t tan omega s by 2. But if we select impulse invariant transformation, the omega p is omega p by t and omega s is omega s by t. The second step is decide the order n of the filter in order to estimate the order n. Here we calculate a parameter n1 which is equal to 1 by 2 log 1 by as square minus 1 divided by 1 minus ap square minus 1 whole divided by log omega s by omega p. Here as is the gain at passband frequency omega p and as gain at stop band frequency omega s. Now select n such that n is greater than or equal to n1. Usually n is selected as nearest integer just greater than n1. The third step is determine the normalized transfer function h of Sn of the analog low pass filter. When n is even, h of Sn equal to pi, k equal to 1 to n by 2, 1 by Sn square plus bk Sn plus 1. And when n equal to odd, h of Sn equal to 1 by Sn plus 1, pi k equal to 1 to n minus 1 by 2, 1 by Sn square plus bk Sn plus 1, where bk equal to 2 sine 2k minus 1 pi by 2n. The fourth step is calculate the analog cutoff frequency omega c equal to omega s by 1 by a square minus 1 whole raised to 1 by 2n. Fifth step, determine the unnormalized analog transfer function h of s of the low pass filter. H of s equal to h of Sn at Sn equal to s by omega c. When the order n is even, h of s equal to pi, k equal to 1 to n by 2, 1 by Sn square plus bk Sn plus 1 at Sn equal to s by omega c equal to pi, k equal to 1 to n by 2, omega c square divided by s square plus bk omega cs plus omega c square. And when n is odd, h of s equal to 1 by Sn plus 1, pi k equal to 1 to n minus 1 by 2, 1 by Sn square plus bk Sn plus 1 at Sn equal to s by omega c equal to omega c by s plus omega c, pi k equal to n minus 1 by 2, omega c square divided by s square plus bk omega c s plus omega c square. Sixth step is determine the transfer function of digital filter h of z. Using the chosen transformation, transform h of s to h of z. When impulse invariant transformation is employed, if t less than 1, then multiply h of z by t to normalize the magnitude. Seventh step is realize the digital filter transfer function h of z by a suitable structure. Eighth step, verify the design by sketching the frequency response h of e raised to j omega. For getting this h of e raised to j omega value, put z as e raised to j omega in h of z.